Well, here's, hold on, I'm trying to open the pen cover with one hand. This pen has ink. So here's a problem I've been working on, an interesting one. I call it the Blackbird Problem. Actually, it would probably be better to call it Pigeon Problem. And it goes like this. Suppose you have a wire, the kind you see outside, you know, a pole, that kind of thing. And you have some birds on this wire. So bird one, you know, funny looking thing. He's got a beak, he's got a nose, you got a couple of them. And I'm gonna label these birds 1, 2, 3, 4, 5, 6. And I could label them to any numbers I like. There are as many birds as I want. This is a very long pole. Now I have relationships between the birds. The birds are friends with each other. So I say, I'm going to draw this in a graph. I say that bird 1 is friends with bird 3. Bird 1 is also friends with bird 4. Bird 4 is friends with bird 5. Bird 5 is friends with bird 6. Bird 6 and bird 1 are having an affair. Bird 3, oh, there's no 2 in here. And bird 2 is friends with birds 5 and 6, but not with any of those. Actually, I could make it symmetrical just for fun, you know, just for fun. Bird 3 and bird 4 are friends as well, to make it kind of nice looking. The problem is, how do you arrange the birds on the pole? That is to say, which bird comes first on the left, which bird comes next, and so on, so that the birds that are friends with each other are close to each other. That is to say, the distance between friendly birds is minimized. So by distance, I mean, suppose that I arrange the birds like this. I'm just randomly going to pick one now. 5, 4, 2, 1, 3, and 6. So I have this arrangement of birds on the wire in this order. 5 is on the left, 6 is on the right, and then the rest are in between like that. Now I say the distance between 5 and 4 is 1. The distance between 4 and 2 is 1. The distance between 2 and 1 is 1, and so on. The distance between 5 and 2 is 2. The distance between 5 and 1 is 3, and so forth. So now you can tell the distance between any two birds. But I want the sum of the distances between bird I and bird J, where bird I is linked to bird J in the graph G. So that is to say, I want the sum of the distances of bird I and bird J, where bird I and bird J, this edge, is a member of this graph. The graph is just edges and vertices and so on. And in this case, we can evaluate how well I did with this random one. So the birds 1 is connected to 3. I'm going to write them here so I don't forget. Actually, I could just cross it off. So bird 1 and bird 3 are friends. The distance between 1 and 3 is 1. Bird 1 and 4 are friends. The distance between 1 and 4 is 2. Bird 1 and 6 are friends. The distance between 1 and 6 is 2. Bird 4 and 5 are friends. The distance there is 1. Bird 3 and 4 are friends. The distance there is 3. And bird 5 and 2 are friends. The distance there is 1. No, 2, sorry. And 2 and 6 are friends as well. The distance there is 3. And the sum is 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. I probably counted that wrong, but it's close enough. Anyway, so this here has cost 14. The goal is find a way to do it better with a lower cost. That's actually a really low number. I probably managed to hit randomly on something that's pretty good. But let's try another one randomly. 1, 3, 4, 5, 6, 2. So let's try that one. The score of this is 1 and 3. Distance is 1. Hold on. It's handy to put these because it's easier to add up. The distance between 1 and 3 is 1. Distance between 1 and 4 is 2. Distance between 1 and 6 is 4. Distance between sorry, 1 and 4, 1 and 6, 4 and 5. I better cross these out. Is 1. Distance between 5 and 6. Oh, interesting. I didn't do that last time. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Oh, you're right. I actually missed 2 of them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 5 and 6. 1, 2, 3, 4, 5. There should be a 5 in here. Which means that this score is actually not 14, it's actually 19. Okay. Anyway, this one. Let's see, what do we have? We have 1 and 3. 1 and 4. 3 and 4 is 1. Oh god, I'll just start over. Distance between 1 and 3 is 1. Distance between 1 and 4 is 2. Distance between 1 and 6 is 4. Distance between 3 and 4 is 1. Distance between 4 and 5 is 1. Distance between 2 and 5 is 2. Distance between 2 and 6 is 1. Distance between 5 and 6 is 1. And I think that's 1, 2, 3, 4, 5, 6, 7, 8. That's all of them. I think. 3, 6, 7. Yep, that's right. And the total sum is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in fact, this here has cost 13. This one has cost 19. So you can see, just by rearranging some of the numbers, we've reduced the cost. And can we do better? Is there a way to rearrange it so it gets even lower? Can I get it less than 10? I don't know. And now, this is just a small version of the problem. What if I had a very large number of birds? I had 10 million birds. And this graph here, the relationships between the birds, suppose I say that each bird is friends with up to 10,000 other birds. And this would obviously become so enormous that I could no longer draw it on paper. How then do I rearrange those birds to lower the score? And an alternative problem, or a more interesting one, is what is the smallest score that I can get? How do I know that I can't do better? So for instance here, the score is 13. How do I know that this is the best one or not? What is the lowest possible score that I could get? I mean, these are a lot of interesting problems here related to blackbirds. Actually, I should probably say that this is not really related to blackbirds. It's related to packing, packing boxes essentially into a conveyor belt. But the boxes are allowed to send messages to each other. So suppose you have, the birds are parallel computers, and you know that each of these computers wants to talk to the others to send messages, some of them more than others. How do you arrange them so that the distance that they have to transmit their messages is reduced if you only have one wire?